the next question we're going to try to answer is, how do we know that recursive functions are correct? And here I'm going to define this ideal of the recursive leap of faith. And basically there are three main steps to the recursive leap of faith. The first thing you do is you verify that the base case is correct. Then you assume that the function overall works. Assume that whatever recursive function you are defining is defined correctly, and then using that, check that the recursive case is correct. The reason we need to assume the function works is because the function is used in the recursive case. So let me go through the recursive leap of faith with the factorial function. Well, what we do is we first check the base case. If n is 0, is it true that 0 factorial is 1? Yes, that is correct. So now we're going to assume that factorial is correct. If we know factorial is correct, then we know factorial of n minus 1 is computed correctly. And then now we just have to figure out that factorial of n can be found correctly by just calculating n times n minus 1 factorial. And is that true? Well, yes, that is true. So that's an example of how the recursive leap of faith works, and it really helps in saving time with a lot of tricky recursive problems. If you just assume the simpler cases of the problem will be solved for you, you can focus on the larger problem. And some of you might be wondering, how does this voodoo magic work that we can just assume the function that works? Well, at the heart of all of this is a principle called in math called mathematical induction. And mathematical induction is a very nice way to prove certain mathematical ideas, and I'm not going to talk about it too much right now, but maybe later if I have time, I will definitely do a video on mathematical induction because I think it's really cool. Recursion and induction are very closely related. In fact, the reason recursion works is because of induction. So it is a very cool topic. And if you ever do decide to pursue a computer science degree or go deeper into computer science, there's this one class that you always take called discrete math and probability maybe. And in this discrete math class, one of the first things you'll learn is mathematical induction. And in Berkeley, that class is called CS70. And it's really, really cool stuff. So, now let's say that you aren't a person of much faith and you don't believe in the recursive leap of faith. So you want to figure out, hey, how does this work at the end of the day? Like, how can I get the details of exactly how factorial works? So this is what this is for. So, well, when we call factorial 4, what really happens? We check if n is 0, it's not, then we return n times factorial of n minus 1. Let's do that. 4 times factorial of 3. Well, now we have to call factorial of 3. What happens when we call factorial of 3? We get 3 times factorial of 2, and so on. And then when we call factorial of 2, remember, none of these have actually returned anything because we don't know what factorial this returns. We haven't reached the return statement that returns anything other than another function call. So this is the key idea here. We get to factorial of 1. We don't know what factorial of 1 is. So it's this, we know it's 1 times factorial of 0, but we don't know what the actual value is. And then once we get to factorial of 0, now we reach the base case. N is 0, and we return 1. So factorial of 0 returns 1. And then that then solves this problem. What's factorial of 1? It's 1 times 1. And we get 1 here. What's factorial of 2 now? 2 times 1. Factorial of 3 is 3 times 2. And then factorial of 4 is 4 times 6. And there's our answer. So this is how internally the recursive factorial works. And to further hammer this home, let's look at the environment diagram for this. So in the global frame, we define the factorial function. And now we call it. So you might have wondered, hey, how is it that I can call the function that I haven't even finished defining? And the reason this works is because we define it actually in the global frame. So the function is defined. So now we ask ourselves, we first check, is n 0? It's not. And now we go to the else case and we return n times factorial of n minus 1. Well, hey, we have a call expression, so we have to create a new frame. So there's no return value. Usually we see that the function has a return value before we go to the next frame, but now we have no return value. So again, same process. We call factorial of 2, then we call factorial of 1, then we call factorial of 0, And now we're finally going to get into the if case, and we're going to return 1. And now where do we return this to? We return that to right here, and then we multiply n times factorial of n minus 1. Well, what's n? N is 1. And so once we return that, we're going to get the return value of 1 here, and then the next one is going to be 2 times that. So we're going to return 2, and then we're going to return 3 times 2, and then we're going to return n times factorial of n minus 1, which is 6. So that's 4 times 6, and that's 24. And there's our final answer. So this is how it works in the environment diagram. And I'm showing you a lot of these many different ways to look at it, because recursion is a little confusing of a topic when you first see it, because it's kind of counterintuitive to be able to define a function based on the function itself. And the last thing we're going to do today is I want to go through one example of recursion. So this is a fairly simple example of recursion, and next time we'll be talking about more complex examples and some of the cool stuff you can do with that. But this is just the basics. So take a crack at this one. It's okay if you can't do it though, because obviously this is the first time you've ever learned recursion, or those of you that have learned recursion, this is good practice still. So what we're going to do is we're going to write a function that takes a number and returns the sum of the digits of that number. Alright, so I'm going to call this function sum digits. And I encourage you to do this however you want. You can sometimes define the iterative version of the function first, and then define the recursive version. So, actually I'm going to do exactly that. I'm going to define it iteratively first. So just so we can see how it all works together. So I'm going to define sum digits iter of n, and then how do I define this iteratively? Well, I have an initial result. This is going to be my sum, and then while it's the case that n does not equal 0, I'm going to take out the last digit, and then each time I'm going to rebind n and the result to n divided by 10, n divided by 10, and then the result plus the last digit, because I want to iteratively add the last digit, and we're going to keep on going until we have 0. And then what do I do at the end of the day? I return the result. So I'm pretty sure this will work, so I'm not going to test it. Now, the recursive version of this function is a little more interesting. So the first thing I like to do when I do recursion is I think of the simplest possible case. What's the simplest possible number I could have? Well, the simplest possible number I could have is any one-digit number. Any one-digit number just returns 4, this itself. And then I look at some more complicated cases. So let's say I have 1, 2, 3. This should give me 6. And then there's some more complicated cases of like 3, 4, 5, and 2. That should give me 14. Right? Yeah. Okay. And now, so those are my tests. Alright, so how should I figure out this function? Well, I already think I have a pretty good base case because I have a pretty simple version of this problem. If it's a one-digit number, I return the number itself. So how do I express the logic that it's a one-digit number? Well, that's pretty easy. I can just check if the number is less than 10. And we're going to assume that we're not going to have any negative numbers. We just return 10. Now, what is the recursive case? So this is always the tricky part in any recursive problem. So let's see how we can figure out what 1, 2, 3 is. Well, notice that when you usually split the number into 12 and 3, right? Because remember, that's exactly what we did in the iterative version. We split it up into 12 and 3. Notice that the sum digits is just the sum digits of this number plus the last digit. And we can keep on doing this. So again, we take that same idea. 3, 4, 5, 2. We split it into 3, 4, and 5, and then 2. And then notice that the final answer is just the sum digits of this number plus this number. So let's take that exact logic. So I'm going to define a variable, all but the last. And I'm going to define the variable last. And then all but the last is just going to be n floor of 10, because that's how we get everything but the last digit. And our last digit, of course, n modulus 10. And now, what do? Well, I return the recursive sum digits of everything but the last digit, and then I add the last. And this is, again, a natural recursive definition of this function. So, in reality, this is just 3, 4, 5, 2. So sum of this thing is just going to be sum of 3, 4, 5 plus 2, right? So we're just slowly taking this down into a simpler version of the problem. And that's how this function works. So let's just quickly do the doc test for this, and everything works. Alright, so this is the example of sum digit recursion, and I do want to warn you real quick. In recursion, just like in iteration, it's possible to have an infinite loop. If you don't have a base case, or if you have a base case that's or let's just say I don't have a base case, what happens? You're gonna get something pretty scary. Alright, I'm just gonna do it. Hopefully my computer doesn't die. So if I call factorial recursive on like 5, this is what happens. It's just going to keep on going because there's no point in which the function ends. And there's no base case basically. And thankfully Python has a catch for this in that the maximum recursion depth is exceeded. So basically we just had an insane amount of calls to factorial recursion because again, we're not approaching anything that's going to end, you know? We're going to keep on trying to return things, but we're not going to get anywhere where we can actually return something. So be careful when you're writing recursive functions. If you ever get this, that just means you have either an incorrect base case or your base case doesn't exist. Alright, that's all I have for today. Thanks for watching. I'll see you next time. And next time we'll look at some more complicated recursive examples and also another idea in recursion called tree recursion. Thanks.